Assalamu alaikum and welcome to our presentation. In this presentation, we will be presenting the assignment 2 for industrial power electronics. The team of ours is formed by MUSFIQUR RAHMAN and Neshan AL LEELA KANNAN. Today, I am going to explain the operation of the feedback controller in buck converter as shown in this block diagram. A buck converter is a type of DC to DC converter that steps down a higher input voltage to a lower output voltage. The diagram here represents a closed loop control system, which ensures that the output voltage remains stable and matches the desired reference voltage, regardless of changes in load or input voltage. So from here, the objective is very clear, which is to understand the operation of the closed loop control system in a buck converter. From the picture itself, we can break down the blocks into several parts, which are error detection, PI controller functionality, PWM signal generation, switch operation, filtering, and feedback. The overall transfer function is given below. The first part, to explain the first part, error detection, the process is to the output voltage V out is continuously measured and compared with the desired reference voltage. The difference is calculated by this equation, which is V error is equal to V out reference minus V out. The purpose is to detect deviation between actual and desired output voltage. Up next, PI controller. The error is processed by the proportional integral PI controller, which generates a control signal VC to correct the error. The PI controller adjusts the control signal based on the both magnitude of the error, proportional action, and the accumulated error over time by integral action, ensuring a stable and accurate response. The transfer function of PI controller is given here. Kp is the proportional gain and Ki is the integral gain here. Furthermore, for PWM block, the control signal Vc is fed to the pulse width modulation block, which converts it into duty cycle D, a time-based signal that determines how long the switch remains on and how much for the time it will remain off. For the next part, switch operation, the duty cycle controls the energy transfer from the input to the output by modulating the switch, effectively producing an immediate signal equal to V in into D, which we calculate by V output is equal to V in into D for this particular block. And for the next one, filter, the signal is then filtered by LC, inductor and capacitance, filter to remove the high frequency components and deliver a smooth DC output voltage to the load. The filter also helps to regulate the dynamic response of the system to sudden changes in load or input voltage. The last operation is feedback loop. The output voltage V out is fed back to the error detection block. It ensures the system continuously adjusts the duty cycle to maintain. It handles disturbances in V input or load, maintaining stability and precision. In summary, I would like to say that closed loop control ensures stability and accuracy in buck converters. Feedback mechanism allows for dynamic adjustments under varying conditions. It is widely used in DC to DC conversion of power supplies, renewable energy system, and embedded electronics. For the rest of the parts of the presentation, I would like to pass it to my teammate.
A very good morning to everyone. Today, I'm here to give a presentation about my do a video about my second question progress, which is design a switch SMPS model with a DC output voltage of 30 to 50 from single phase, which is voltage of 240 VRMS for input voltage is 240 VRMS and with a 50 Hertz. The DC-DC converter rated power is 100 watt and the output voltage factor is steady state must not exceed 2%. Okay. The information of my design is the voltage input is 240 VRMS. The frequency I chose is 40 kilohertz, and voltage output is I chose is 40. Then the voltage ripple factor is 2%, power is 100%, and the design of SMPS is I choose buck converter open loop with MOSFET. Okay, first we need to find out the parameters with using a theoretical calculation method, which is by using like in this word I have done. This is first you must find the transformer, which is the primary side, the secondary side, and we need to find the N. Then we need to find the duty ratio. We need to find the resistor. Then after once done, the resistor you can find by using the power formula only, or you can use first you find your current, then find the voltage also can. Find by the VIR formula also can. Then there's a minimum inductance which is L min. So we need to first get the L min first, forget the actual inductor current, which is the inductor current is more larger than L min, which is about 25%. So we need to times 1.25 with the L min. So we get the actual inductance value. Then we get the inductor current by using the formula. So then capacitance. Then we get the IL max, maximum current inductor, maximum current, minimum current inductor. Then we can find from the maximum and minimum inductor current inductor, we can find the average inductor current. Then we also do a volt by using a formula. We also find voltage output ripple. Okay, we get all the value from this calculation. Once we get the calculation value from this calculation, we start to do design the SMPS in MATLAB, which is it's wait I will show in the MATLAB. Okay. This is my design of the buck converter of a open loop SMPS model by using a MOSFET here. So first we need to set the parameter, design like this and set the parameter or the AC voltage. I set the parameter, which is the peak voltage is 339.41 by the using the formula in the calculation. And also calculation and 39.41 voltage, and the frequency was 40 kilohertz. Okay, once done setting that, and you need to set the transformer by using the N, which the N I get is 5 from the calculation. So I choose 1/9, the ratio. Then you need to just connect the measurement of the voltage to find the to find the VS here. Need to connect the voltage measurement at here. And next, we need to calculate, connect the current measurement at the diode to find the current diode. Then you need to also connect the current measurement at the inductor to find the inductor current. And then you need to also connect the voltage measurement at the V out to find the how much V out was get at the last. Okay. And here we have the scope, and this is the GoTo, which is they have a signal connection between the scope and the circuit results. And here is the carrier signal and data, and the K I set for this is 0.566, which is the duty ratio of the circuit. And the resistor I set is 16. And then capacitance I said is both capacitance I said is 15.63 microfarad, and inductance I said 108.8 microhenry. And once I set all, okay, I run. Then from the running, I can get the before that we need to set the power wave to discrete, and the sample time is 1 micro. So that's all. Once you set 1 microsecond, you set. After you can run. After run, okay, you can get the result by seeing the scope. When you run time also, I just connect the display here to see the measurement of voltage for VS and which VS we input and V output, which is V input I get 67.09 and V output is near to the 40, which is 39.36. If you see, wait a minute, I'll open the scope. Okay, this is the voltage measurement waveform we got for the 4 measurements, which is VS, which is the yellow one is VS, red one is VO, blue one is ID, which is current diode, and orange is current inductor. So when I just make a bit, okay. Okay. Okay, now you can see the, wait a minute. Now again, you can see the maximum voltage for voltage input. We get 67.09, which is near to 70, and minimum is 64.66, which is also near to 70. Then when we go to voltage measurement one, the wax we get is 39.16 it's near to 40, and 38.89, which is near to 40 also. Then the current measurement, okay, which is the blue one. Okay, the blue one we got maximum is 3.95, 959 ampere. Then minimum we get 0.05819 ampere. Then the orange one we get max is 4.179 ampere, and the minimum we get is 0.7724 ampere. So when we enlarge, when we just make it go deep, so wait a minute, just go make it deep. Okay, this is the waveform. Wait, I will just make it again. Make it nice. So as you can see the waveform, which is okay. So this is VS. So this VO, when it's going up, the VO is going down, and when the V in is going down, the V output is going up. The waveform. That's all. This is look like a sawtooth waveform. The current measurement one. Same goes to the current measurement two also. It's ID and IL. So this is the waveform we get from the circuit. And the second one, the second scope, which is the for the signal gauge signal in the scope. So scope 5. Okay. When you open, okay. Okay. So I open the gain first. So the gain we got max is 5.6, which is we set the duty ratio to 5.6 just now. So we get the result max and min is 5.66. And repeating sequence is 1.0 max and min is 0.0. And regression operator max is 1.0 and min is 0.00. So, and I go. Okay, now you can see the waveform form. So this is the gain, which is 0.566, and the blue one is the signal. If you see, it's in a shape of a sawtooth. Here is in a shape of a square waveform. So that's all from the second Roman questions answer for the MATLAB. And after this, I'm gonna explain about the fourth Roman question, which is, because before that I'll explain about something in the third Roman first. So when design, okay, we got the result like this. So we calculate the V voltage input average and ripple input voltage. We calculate, so we get 65.7, and the RC, sorry, RC we got 3. Then voltage output we got average output is 39.25, and the ripple voltage output RC is 2%, and ID we got is the ID we got is, you see the ID, okay, the average ID we got is 1.95, and current ripple ID is 3.901. So once with that, We go for I value also. So IL we get 2.48 for the average current inductor, and inductance we get 3.407 by calculation for the simulation. So this is the simulation just now I said about the signal and gains all. So we got the value also max and mean, same goes. Then we make a comparison, which is about the calculation value and simulation value. The average input voltage 70.7, 6 point, not a big difference. And duty ratio also not a big difference. And report voltage also we saw not a big difference. And 40%. Okay, I mean 40 voltage is and 39 input voltage not difference, big difference. 2%, and 2.53 ampere, 2.48 ampere, 4.54, 4.179, 0.5, 0.7, 4.8, and 3.407. So it's the result we get for the calculation and simulation was not have a big gap for the result, but it was near to the calculated and simulation value. So after that, we can see the fourth Roman question of the second one. Second question, fourth Roman. So this is also using a MATLAB, but we need to design a stable converter feedback controller, a program which is using integral PI in the design, and we need to get some of the result from the design. So first we need to create a PID controller, which is like in the picture. Okay, I show in the MATLAB. Okay, we see the MATLAB. Okay, this is our design of the controller. So we need to create first. We need to create the subsystem one, which is the PI control first. So in the PI controller, we need to create like this, which is the first one. The first thing we need to put is our gain we choose. So the gain, the KP and first the KP and KI I choose is 0.33, and KI I choose is 10,000. So we need to design like this. Once done this, we need to go to the subsystem to PWM. So in PWM, we need to just create like this with the gain is 1. Then once done this one, we need to create the subsystem 3 about the buck converter. So buck converter, we need to create like this. Okay, this one I will explain in the word in my report, which is the calculation was described at the how to get the value of this transfer function. So the gain is 1. Then once did this, okay, you can run it, and when you run it, okay, once you run it, you can open the linear measure manager. Once linear measure manager was opened, there's a board diagram. I mean a board plot. So on the board plot, you need to measure the phase, the angle, frequency, all. So I don't want to show you here, but I can show in the word because it's a bit late time. It will make a delay. So before that, so this is the calculation, the formula which is I use for the transfer function in a subsystem to PWM, and this is the KP and KI choose for the gain value, which is this is the KP and KI, which is the old one, okay, original one. So just now I say about the transfer function. So we just put this one on, we set up with this and the pair controller. Once we set up all of these, okay, I run the board diagram. So once I run the board diagram, I got the phase degree is 140. Why I choose 140? Because the phase margin I chose is 40. So 180 minus 140 is equal to 40. So that's why I chose phase degree is 140. We see in the board diagram plot 140. Then the frequency 2.4. So once I get 2.4 frequency, I need to search the 2.4 frequency same at here to get the point of the magnitude. So the magnitude I get is 47.2, which is not stable. So after that, I need to put the frequency magnitude, this one, to the waveform of the middle of the zero phase, zero magnitude. So from that, we can get the frequency, real frequency 1.24, exponent 0.5. So from there, you can get the phase degree. phase degree, which is we need to straight go to the down for the phase degree angle. So if you just go down until here, from there the dot was here, so it showed that the phase degree is negative 1.92. So once done, you can open up the pole zero at the same linearization map. So from there you can see the pole zero map, which it was a left plane, left half. So we can see there was a 4 point, but the zero was here, and there was three pole 3x at the down. So we can see, okay, after that, after get that information, okay, you can now calculate the crossover frequency, which is a crossover frequency I get is 124 kilohertz. Yes, now you can see here 124 kilohertz. So with that, divide by 2 pi, I get 19.74 kilohertz. Okay, with that, I get the phase margin, which is negative 192 plus 100. So I get negative 12. So the all DC gain I use is 80 dB. So from that 8 dB, we need to shift down. So new DC gain we must get, because just now the old DC gain is not stable as well. So new DC gain is 80 minus 47. This is the old one. So old gain, so which is magnitude also 80 minus 47, 2.2. So we get the 2.8 dB. From that, we can get a new KY by using these formulas. So we get 43.65. So from here 43.65. We get KI. Now we need to calculate the KP, new KP, or make a new stable connection. So from KP, we do KP old divided by KI. So we get 43 points. So we get the KP is 1.44 milli. So so new KP is 0.00144 and new KI is 43.65. Okay, once done, once we get the new KP and new KI, okay, we need to change the KP and KI at here, which is at the Simulink MATLAB. So wait a minute. Okay, at here. Wait a minute here. Okay, right here. So we need to change here. So just now I say 0.00144. Okay, and here we need to change 43.65. 43.65, and once done, run it, and you will get the board, and you will get the blueprint one, which is like this. So we need to search the diagram. Sorry, this one we get a problem at the board diagram, so I can show, because once I leave it the alignment, the writing on the box was just disappear like that. So I can show you, but I can show at the word in the report. I mean the report. So once we just change the old KP to new KP and KPI and KI, so we can get the new KP and KI. So I just make a same also 140. Just choose the same phase degree, which is 140. Then I get the frequency is 2.4. So from that I get the zero magnitude, which is about 2.43 frequency, and the phase degree is at 123. And that's all. Okay, 23. Then we need to calculate the, and then this because the board diagram is more stable, and from that pole zero map. Okay, pole zero map. We was calculated, and we got the pole zero map, which is about this result, which is more stable. It's all half but more stable. So once done that, we open the new crossover frequency, which is we get the new crossover which is 3.87 kilohertz, and the new phase margin is 57 degree. And MATLAB, this is the MATLAB same link. Okay, we need to create from the Buckhorn method. So I place the this one into into uh, into the PI control in the MATLAB. So wait, I show it. So testing 2. So if you see, open this, you can see my value is here 0.0144 and 43.65 here, and go back. Okay, so once you set the same as set for the testing for the second question, the same value you need to input, and here's my voltage reference 40. So once I done, I run, so I get the V out is 38.75. It's near to the voltage output, which is a 40. So once I run, so I get the waveform like this. Okay. Okay, I get the waveform like this. So I get the V input is 6.67.09, which is near to the VS calculation with 70, and the mean is 65 voltage, and the voltage measurement we got is which is a V output we get is a 37.03, which is near to the 40, and 36.30 is near to the 40. And current measurement we get is 3.87 ampere, and minimum is 6.34. And once done that, and we go to the current measurement one. So here we get is it is about IL. Just now is about the current diode. Now current inductor, which is 4.067, and minimum is 5.43, 0.5439 ampere. That's all we get result. And once we done, we go to the scope, another scope display or scope, which is this is the signal one. So we got the saturation is 1.0 for max and minimum 0, and repeating sequence we get same also. So wait a minute, I will just adjust it. So delay. So this is the result. Sorry, it's a bit lag. So this is the result we got from the signal we put for the carry signal, array signal, and switching frequency. So this is the result. This is switching frequency. Okay, so we get the result from the design as well. Okay, now it's coming. Okay, wait, I need so okay, now it's come ready. Okay, so saturation is 1.100 for max, and mean is 1.10, and repeating sequence is 2.02, max is 2 and mean is 0, and the repetition operator is 1.00 and mean is 0.0. Okay, we get that's all the result we get from here. So once done, we go to the report first. Okay, once we calculate, we can already get the result. So this is the result for the voltage input, and this is for voltage output, and we get voltage output is 36.67, and New ripple voltage is 2%, and IL is 2.31, and new ripple induction IL RC is 3.52 ampere. And that's all. So from here we can see the cross friction is a lower, switching frequency is, and this again there was a high gain even though low frequency. Phase margin is 48 degree. This RC 40 is map is left hand plane, and overall is 140. And the correction before correction 124 kilohertz, 80 dB. Now negative 12 degree. Left half plane is okay. And overall no. Stability is no. This again yes. Phase margin no. 40 map yes, and overall is no. And after correction we may have made is a 24.3 kilohertz, and the DC gain is 32.8 dB, and phase margin is 840 degree, and 40 map is the left half plane, and overall is yes. Okay, the stability is now all. That's all from my part of the present I need to give. And I thank you for listening my presentation. Thank you.